All right, let's do it. Okay, we're going to do some geometric proofs now. So the last video we walked through algebraic proofs, right? That was using past knowledge of algebra. Now we're going to start to transition. So more and more of our proofs become geometry. But we have to slowly introduce that. We don't want to just throw a bunch of geometry and be like, glue this all together. So what we're going to do is our proofs are really going to be heavily algebraic right now. But we're going to introduce one or two things we'll use from geometry, okay? So that's the big idea here, transitioning to geometric proofs by just bringing a few pieces in at a time and practicing them with proofs that are still mostly algebraic, okay? One other big thing, it won't come up that much in this video, but as we move forward, you'll notice definitions are the way to transition from words to geometry. So for example, in the beginning of a proof, if it says like M is the midpoint, right? So if like literally if it says, wow, that is a big thick pen. Okay. So if it says M is the midpoint of ... the only way you get from the word midpoint to anything afterwards, like for example, like AM is equal to MB, that would be the definition of the midpoint. Or the line segment is congruent to the line segment. In this book, that's a theorem. I'd be okay with you just calling that the definition of a midpoint and it having two different definitions that are equivalent. But that's the idea, is to get from the word midpoint, or to get from the word right angle to 90 degrees, or to get from the word perpendicular to it makes a right angle. Anytime you have a word and you want to use the meaning of the word, that's the definition of midpoint, is the justification for that step. And that's going to really help us, especially at the beginning of end of proofs. So let's just throw out a couple useful postulates and theorems. So this was the video I did on linear measurement. It's just saying, if we have a line segment, we could line up a ruler so that the 0 aligns to one side, and then the other side has some positive unit of measure, right? We could, scale the ruler so everything, this line segment is of length 1 and every other line segment is based on this one unit. Or we could use inches, miles, meters, whatever measure, right? So the ruler is saying we can measure line segments lengths, okay? And then segment addition postulate, this is our bread and butter, right? We're basically never going to use the ruler postulate, but it's a fundamental assumption we all agree is that we can measure the length of a line segment. So it's crucial, and yet we'll never state it as a reason in a proof. However, the segment addition postulate is basically all we have. That's all we're going to use. We're going to use it in half of the proofs or more in this section, okay? So all it says is, it's basically just kind of the definition of between, right? It's saying if these points all lie on a line and B is in between AC, well then we can add up a part plus the rest of the part, and because they're on a straight line, then that equals the total of AC, right? I didn't veer off the path and make a triangle and take a longer route. I went directly 2 and then a directly 3, and that was a total direct length of 5 because they're collinear and B is between A and C. Okay, that's the idea. But we're going to use that a lot. Again, these are all numbers, numerical lengths that are equal. This is algebraic. This is all algebra. This has nothing to do with geometric, well, not nothing, but this is not stating geometric objects add up. That doesn't make sense. Bird plus rock can't equal chair or something, okay? All right, and then we have this theorem. All these are provable. All we do is use the definition, like we could prove it. We go, okay, so if we start with AB, right? We go, okay, well, how would you prove that to be itself? Okay. Oh, I know how you prove it. I was starting in reverse. That's why. I want to end there. So we'd say, well, the length AB, any number that is equal to itself, AB, right? That's the reflexive property of equality. We have that property from algebra. And then we go, well, then we know that the line segment AB must be congruent to the line segment AB. And that's the very definition of congruent line segments, right? What's the definition of congruent line segments? Two line segments are congruent if and only if. So it's a biconditional. Every definition is their lengths are the same. So if the lengths are the same, then we know the segments are congruent. So that was a two-step proof. Okay? We could do the same thing with these. They're all based on just getting the property of equality and then using the definition of congruent line segments to say, well, if they're equal, then they're congruent. So that's how you do all of these proofs. That's why they're called theorems. So each one is like 2 to 3 steps. I'm not going to go through and prove them all, but that's the idea. Start with the property of equality and use the definition of congruent segments. Okay, but here's the big important idea. These are the only properties that we have with congruence. Literally, right? We're never going to use the symmetric property at all, but we are going to use the reflexive and the transitive property all the time. This is all you have with congruence. You cannot say triangle plus square, right? There's no operation mathematically to add figures together, right? We can talk about figures that are adjacent and perimeters and surface areas, but we don't have a mathematical operator that does anything with geometric objects. All we have is congruence that says they are the same, except for their name and where they are in space, but these are the same. Every measurement you could make, everything, you could put a ruler in any direction on this thing, it is the exact same as that other thing. It's just named differently. That's the idea of congruence, and we only have 3 properties, and we will use these all the time, or at least number 1 and number 3 there, okay? All right, and then kind of a big idea for proofs, just to kind of give you an idea of how we're going to work, especially at the beginning, is it's really common that we start in the world of geometry, right? So the given is over here in the world of geometry. We're given this midpoint, we're given this, and then what we do is we go, we need to use a portal, a wormhole to travel to the world of algebra, and that is the definition. And we open this door, we rip asunder the dimensions, and we travel to this alternate universe, this world of algebra. And now we go, oh, look at this. M's the midpoint of AB. So we know that, and we have this picture here. M is the midpoint of AB. So we go, oh, we know this by the definition of the midpoint, right? And then we go, oh, and this were some notes I was writing over here. Let's use, so the definition of the second one would tell us, oh, we know that B is the midpoint of that. So we go, oh, well, that means MB equals BC. And again, what let us get from a word over to algebra, equality? That was the definition that traveled between the world of geometry and kind of math or algebra. So we can say, yeah, we know that's true by, again, the definition of the midpoint, okay? And then, well, what else could we do here? How could we want to get this thing into world of geometry that 2 things are congruent? We want to get that AM is the same as BC, the line segment geometric objects. Well, what could get us there is if we could get that AM length is equal algebra number equal to length BC. If we could get there, then we could use the definition of congruent segments, right? Because if 2 segments have the same length, then they're congruent. Or, I mean, it's a biconditional. It could go either way, right? If they're congruent, then line segments. But the definition is what takes us from the world of geometry to the world of algebra. And it's really common that we'll start in geometry, we'll jump over to algebra, we'll do all this cool solving, and then we'll just jump back over to geometry for the final answer to say, I just proved something geometrically. But really, I wandered through the realms of algebra with my compadres on these wild adventures. Okay, so let's actually do this proof. So we have the definition of the midpoint up here. That was step 2 after, well, sort of, if all those givens were one step. And then we have step 3 there, definition midpoint. So step 4 would be, well, look, they're both equal to MB. So step 4 would be that this is right here. That's what we want. Step 4 would be AM is equal to BC. How do we know that? Well, we could do 2 things because we're in algebra. We can use the substitution prop of equality, or more specifically, AM was equal to MB and BC was equal to MB. So they're equal to the same thing. So they're equal to each other by the transitive property of equality. So either answer there would be good, but I just wanted to give you the big picture here. I didn't rigorously set this proof up. It was just an example to show you that the way you get from the beginning to end of a geometric proof can be to use a definition to go to algebra, do cool algebra, and then use a definition to get back. Okay, let's actually start doing some proofs now. All right, so prove the following. So we're given JK is the same as KL. We're given that HG, so I have to use a different number of slashes now, is congruent to GH. And then you're also given that, I'm just going to use kind of a different pencil here, is that KL is the same as HJ. So it's the same as this. Okay? So what we want to show is that those two are the same. So let's go ahead and start. So first off, and now you have a couple options here. You could either write the given separately or together. I'm going to write them all together, and sometimes that's useful, sometimes it's not. Okay? So I'm only going to pull in givens as I need them. I'm not going to just throw all of them out there and then not use them until step 5. So which two do I want? Well, I'm going to use this one and this one. And together, because they're both the same as KL, I can say that JK is the same as HJ. All right, so I'm going to start with that. So I'm going to say I was given that JK is congruent to KL. And I could either put a comma or a semicolon. I'm going to write it on a separate line, though. I'm going to say KL is congruent to HJ. Okay, and the number 1 was given, even though it was 2 statements. Both of those were given. Okay, step 2 is I'm going to link those together now. And I can say, well, let's get rid of the middleman. JK is congruent to HJ, right? They're both the same as KL, so they're the same as each other. And what lets us do that? Remember, there is no substitution. There's no properties of algebra with congruence. With congruence, we only have these 3 properties: reflexive, transitive, and the one we won't use, symmetric. So we can say something is the same as itself, and we can say if 2 things are the same as CD, then they're the same as each other, right? So we're using the transitive property here. So let's go back down. So that was the transitive, and now it's the property of congruence, okay? And then down here we go 3. Okay, well now what do we want? So we have JK is the same as HJ, but we want that JK is the same as GH. Well, look at this. GH and HJ are the same. So what I'm going to do is I'm going to now pull that other given in. So now I'm going to pull in the given that is HJ is the same as GH. Okay, and that was given. Notice that I'm only pulling it in as I need it. Now, you don't have to do this, but it makes it more elegant, more readable, more clear communication. If you just throw all the given in, and then on step 4, you're using something, people are like, where did that come from? They're like, oh, it was way up here, totally detached. That's harder for people to follow, okay? So now I pull in that given, and now we can say, well, if they're both the same as this HJ, then step 4, I can say JK is congruent to GH, which is what we wanted. It's in reverse, so if you wanted to reverse that, that's fine. I don't care about left, right. That's technically using the symmetric property. We don't need to do that. I don't even think the book ever uses that. Okay, and again, that's the transitive property of equality. Now, something I just want to show you actually with this proof, because this proof kind of lends itself well, so I want to show you a 2-dimensional proof. So this is a 2-column proof, but really it's linear, right? You're really just saying 1, 2, 3, 4, I'm in a march, when really there's a lot going on. You're pulling in new information along the journey, so spreading this out to 2 dimensions can be helpful sometimes. So I'm going to do that here. Before we go on, I'm going to just pull up and make a new page here. Okay, now I'm going to do that same proof on this other page, okay? So I'm going to go ahead and just copy this problem, and on this blank page here, I'm going to paste it, okay? So let's do the same problem, but in a 2-column proof, or I mean in a flowchart proof, in a 2-dimensional proof. So what we do in this proof instead is we put the statements in a box, and we say, okay, well, I was given that JK is congruent to KL. And I'm just doing the same thing that I did before. I'm saying, well, I was given that, and I was given the fact that KL is congruent to HJ, okay? And that was given. So I was given those 2 pieces, and when our powers combine, and here's how this flowchart shows you, I'm combining these 2 steps. these two together form a new statement. That is, JK is congruent to HJ. Now, I love flowchart proofs. I would prefer that everything was a flowchart proof. Some students think 2 columns easier, it gives them a structure. I find it way harder to grade, that's for sure, because I'm like, where the heck did step 7 come from? And I have to search through this nonsense, and the order is really hard to follow because it's not clear, right? Whereas this, just visually, you look at it and you obviously, you put those two things together, and I use the transitive property of congruence, okay? Now, you say, okay, well, what did I do next? Well, then we pull in this other piece. So this is a totally separate new piece of information that I'm stating over here that doesn't have an arrow coming into it, because what was the reason for it? Well, the reason for it is it was given. So I can just pull that out of a hat because it was given to me. So then that's HJ is congruent to GH, right? And now I can say, well, look at that. These two can combine to say that JK is the same as GH, right? And that was, again, the transitive property of congruence. Now, to me, this is so much, visually, so much more clear, right? We started with like the flow going, okay, we started with 2 givens, they came together, and then we're starting down here, we go, oh, we had to pull in another given, but again, our flow is we're just now linking that together, and it's much easier for me to follow. Like, anyways, I won't go over it, but I love that kind of proof better, and I will encourage you to use that through my videos, okay? So, draw 3 congruent segments and illustrate the transitive property using these segments, okay? So let's go, here's AB is congruent to CD, which is congruent to DE. So, oh, we want to use the transitive property though, so I'm going to kind of get rid of those marks, and I'm just going to say, well, we were given these pictures, and we were told that CD is the same as AB. Oh, and by the way, DE is also the same as AB. Well, wait a second. If CD is the same as AB and DE is the same as AB, well, then we know, right? So here's my like flow of logic. Well, then we know that CD must be the same as DE because they're both the same as AB. So if they're both the same as AB, they're the same as each other, right? And so that's the illustration, that's the example of how you use the transitive property with those segments. Describe how to determine whether a point is between A and C. Well, there's 2 things going on if a point's between, right? So one thing is they have to be collinear, right? They have to be on the same line. That's true. Okay, but still that doesn't tell you whether AC has B here, or B here, or B here. The second thing is we have to know that the journey from A to B plus the journey from B to C, so the 2 parts add up to be the whole. Because that's not true if B's outside, right? 2 plus 7 is not equal to 5, right? Because you're going backwards, then forwards. So you have to double up on this leg of the journey. So you've got these 4 extra units you covered. Okay, so let's move on. Justify each statement with a property of equality. Property of congruence for a lot of these. But let's start. So xy is equal to itself, or is congruent to itself. Well, that's the very reflexive property of congruence that we will use a lot this year. The second one, if GH is the same as MN and MN is this. Oh, this is the one we won't use that much. It's just saying you can reverse the order. So that's the symmetric property of equality. Again, we will not use that often this entire year. If AB is equal to AC plus CB, then what we can do is we can, what did they do here? They subtracted AC from this side to get CB, and they subtracted AC from this side. Oh, well, this is just the subtraction prop of equality. Okay. So let's look at copy and complete the proof. So they're starting us with a structured proof, and we're just filling in the blanks here. Okay, so the given, again, they separated them with a comma. You could have wrote them on 2 separate lines, but the given is just what they gave us, right? So PQ is congruent to RS, And, whoa, that's one long line segment. I meant this line segment, that one. And then the second one is QS is congruent to, and all these symbols matter. You need the lines over those because they're line segments. Then we know that their lengths are equal. That's the very definition of congruent line segments. Okay, so if those are equal then, let's see what we did then. We said PS is equal to PQ plus QS. So that's the segment addition postulate that we mentioned above, that I said it's basically the only thing right now we have to use algebra with. So all it's saying is if there's a line segment, then a piece plus a piece is equal to the whole. That's it. Piece plus piece equal to whole on a line segment. We'll do the same thing with angles in the next video, and those will be just our starting point to really do a lot of algebraic proofs, okay? So let's get down here. So the way we said the entire PS was equal to the piece plus the rest, that's the segment addition postulate. Okay, same thing, the whole RT is equal to the piece RS plus the piece ST. Okay, so I'll just erase those from the diagram. And then the addition property of equality, I'll put of equality there. What did they do to get the addition property of equality here? PQ plus QS, and then substitution to get, and so I know at the end here, the way they got this was congruent. I'm just jumping ahead. That's going to be the definition of congruent segments. And so the statement before, I know the only way to get there right now is that PS equals RT. So working backwards, how do we get PS equals RT? Okay, so how did we get PS equals RT here? Let's look at this. So we have these things that are not the same. But looking up top, we get PQ equals RS and QS equals ST. I don't know why they did the addition property. I totally would have just used substitution here. What in the world did they add to that statement? Oh, I see what they did. Okay. So they didn't start from this. I think they started from this, and they said, what could we add? So we could add QS to both. So often it's harder to complete a proof than it is to structure it yourself, or at least I find it that way. Being like pushed into ruts or tracks is harder to follow. So I think what they did here is they started with either one of these two, and they said, well, I want to get PQ plus QS, so let's add a QS to both of these. Okay, so what they get is PQ plus QS equals, yeah, I think they skipped a step here. So PQ plus QS is equal to RS plus QS. Okay, well, we have over here the RS plus ST. That's what we want. But we could swap out this ST for a QS there, right? And so what we could do is get to the next step. Yeah, they skipped a step. At least in my book, they skipped a step, okay? So I'm going to erase this. And substitution, what they probably did is they went to PQ plus QS, which is what we wanted, equals, and then what they did is they swapped out the QS here. So they have the RS plus, and then they swapped it out for an ST, right? Because QS and ST are the same. So that was the substitution property of equality. I would have actually added another step in here then. And I would have said, okay, well, if PS is the same as this, and if RT is the same as this, then what you could do is you could say F is PS equals RT, and that was F over here. So I'm just scribbling out this last line. So then F would have been substitution prop of equality. And then the last step, G, would have been, well, now we know that PS is congruent to RT. And that's by the definition of congruent segments. I did not like that finish to the proof. That was kind of clunky. They definitely skipped that. There should have been even 2 steps of substitution. because you're substituting the PS into here, and then separately you're substituting the RT in for this side. So really you might even do that in 2 separate steps. So you definitely, or 2 steps of transitive property. But to do 2 substitutions and a definition of congruent segments all in 1 step, that's just sloppy right there in my book, okay? So let's do a proof all by ourselves now, okay? I'll do this one 2 column, and then I'll do the next one with a flowchart, okay? So what we're given here is that AP is congruent to CP, and we're given that BP is congruent to DP. And what we want to show is that the entire line segments add up. So again, we're going to have to do that part plus part equals whole, that property or that segment addition property. Okay, so let's go ahead and structure this. Okay, let's put a little 2 column proof here. We already have the given, the prove, and the diagram, so we're all set there. So let's set up our statement and our reasons, well, as plural. Okay, so step 1, the given is AP is congruent to CP, and I'm also going to state the other given, BP is congruent to DP. Okay, so that was given. Now I want to use algebra, right? Because I want to do the segment addition postulate where length plus length equals, equal sign is algebra. I want to get over to algebra, and the way you get to algebra is use definitions. So right away I want to jump over to, we have equal lengths here, and we have equal lengths here. Okay, the way we got there was the definition of congruent segments. Again, right, like I showed you at the beginning of the video, we go from this this world of geometry to this world of algebra at the beginning of the proof using a definition. We're going to do a bunch of algebra, and then we're going to jump back over with the definition at the end to make our final statement. That's kind of the overall flow here, because we're going to want to end with geometry in this congruent segments. Okay? All right, well now we need to say, well, the whole things add up. So we're going to say, step 3, this does not come from step 1 or 2. This is its own statement that comes from the fact that A, P, and B are collinear. So we know that piece, AP, plus the rest, PB, adds up to the whole thing AB. And since it's the same thing, I'm going to do the other two. CP plus, from P to D, adds up to the whole thing C to D. And that was the segment addition postulate. Okay, well now we've got all the information. We don't need to look back up there. So we've got lots of options here. For step 4, what I'm going to do is I'm going to do substitution here. So I'm going to replace these two. Okay, so I'm going to go down here and I'm going to say, well, I could replace CP with AP. So I'm going to go AP plus PD equals DC. And that's substitution. I'm just in a different color. I'm going to show that instead of CP, I put in an AP there. Okay. And then for clarity, and I'll write the reason for all these. And then for step 5, I'm going to use that again, and I'm going to go down. And now I've got AP plus, and I'm swapping out the PD for something it's equivalent to. And so what's that one equivalent to? Well, PD or DP are the same length, right? The distance between 2 points, it doesn't matter forwards or backwards. It's the same. I'm going to put in a BP there. I replace that one. And now we have, okay, well, we have AP plus BP. Why, that's the same thing we have up here. So now we can say, well, since DC is equal to this and AB is equal to this, we can say that AB equals DC. Or do they want DC or CD? They want CD, alphabetical order. So let's say it's equal to CD. Okay. So for the first one here, we swapped out a value. So that was the substitution prop of equality. In step 5, that was also the substitution. I did the substitution separately. I think it's just more clear. So I think that's helpful. And then 6, the last one is, you could say substitution because we're in algebra, but more precisely, we did the transitive property, right? AB and CD were equal to the same thing. So that was the transitive property of equality. Again, you could absolutely say substitution there. And then 7 is, well, now that we know those two segments' lengths are the same, well, that means the segments are congruent to one another. And that's because the definition of congruent segments. Okay, so next we're going to do essentially the same proof, but with subtraction. That's going to be the only difference, except I'll do it with a flowchart. So I'm going to pause it and leave off here because I got to jump back over to Zoom to meet with my students. But then I'll come back and I'll do a flowchart here. All right, I'm back. Man, for you guys, no time passed. For me, I'm like a year older. No, I'm just kidding. I just did Zoom. Okay, let's do a flowchart proof for this. This is going to be a larger proof here. So I'm going to be really detailed and methodical about it. Let's zoom out a little bit. Okay, so let's start somewhere. Let's start, since I know we're using part plus part equals whole, that's where I'm going to kind of start just stating that. Then I'm guessing we're going to use some substitution, really similar to the last proof, okay? So we're given that HI is the same as TU, and then instead of giving this piece, like the last one where piece plus piece, and then you're trying to get that the whole things add up, we're given the opposite this time. This time what we're given is the whole thing equals whole thing. So we got this whole thing is congruent to this whole thing, and we need to do some sort of like substitution and subtraction to get that the pieces left over. We want to show that this is congruent to this, okay? All right, let's start. So I'm going to start with just adding the pieces up, right? So I know that length HI plus length IJ equals the total length of HJ, right? What lets us state that, okay? So well, that's the segment addition postulate. Okay, and then I want to do some substitution there. So let's pull in one of the givens, okay? Let's do the HI one. So we'll do HI is congruent to TU. That's what we're given, okay? So I'm going to erase that line there, okay? So we know that because that was given. Whoa, I didn't write the given. I just started moving on. So that was my given. Now I can, because I'm working digitally, I can kind of move this a little bit. I want to just kind of move this, and I'll move this down a little bit. And the reason is I'm not going to use the geometric version of that. Instead, I'm going to say, well, that means that then HI must be equal to TU. So if the segments are congruent, then their lengths are equal. Again, that's the definition of congruent segments. Okay, so now I could combine these two, and I could say, well, together, what do these make, right? Together, I can replace the HI here with a TU. So now I have TU plus IJ equals HJ. Okay, so where am I going with this, right? So I've substituted one out, but really what I want to do is kind of link this to the other segment. So I'm going to then use this HJ is TV thing, okay? So let's do that same thing that we just did. Okay, off to the side, we're going to say that other given. Now let's just move this all down so we got more room here. So I'm going to move this all down a little bit. Okay, we have tons of space. Okay, so let's do it right there. Okay, so now what I'm going to do is I want to use my other given. Okay, so we know that HJ and TV are the same. So HJ is congruent to TV. That was given. And what that does is that tells us that HJ is equal to TV. Again, those are lengths, those are numbers. That was the definition of congruent segments. Okay, so now we can substitute. Oh, I never wrote the reason here. That was the substitution property of equality. Okay, so now we can piece these two together, and we can say, well, we can replace the HJ. So now we've got TU plus IJ equals TV. Okay, and again, that was the substitution property. Okay, so now we've used both of our givens. We've linked it to the other segment TV. Well, what does TV add up to? It's add up to TU. It adds up to the pieces, right? So the whole TV is the TU plus the UV. So TU plus OUV. So that's how we're going to get it. We want to get that IJ and UV are the same. So what we're going to do is over here, I'm going to say, well, I also know, I'm not pulling this in from other places. I also know that TU plus UV, right? That's just piece plus piece, T to U and U to V add up to the whole thing TV, right? That's the segment addition postulate. That's piece plus piece adds up to whole. And now look, we can put these two together because they're both equal to TV. So you could call this substitution, but most specifically what we're doing is transitive property. They're both equal to the same thing. So the transitive property of, and we're using algebra, this is equality, says that then the TU plus IJ is equal to the TU plus UV, right? And then what do we do next? Last step there, well actually, it's going to be second to last step because we got to get back to geometry, is we can now say that ij is the same as uv. And how do we do that? Well, we just subtracted the tu here and the tu here. So that was just the subtraction prop of equality. And then the last step, here's the nice thing about flowcharts, you can go in any direction. So the last step then is if those lengths are equal, well then we know that the segment ij is congruent to the segment uv, and that was by the definition of congruent segment. So hopefully you like flowchart proofs. I think it really helps following, because if you do this in a 2-column, oh my god, it's like, well, step 2 and step 5 and step 7, and trying to go like linearly and be like, well, in this step down here, and by the way, in this step down here, and then this step and the other step, and it just gets so hard to follow. And people don't draw those arrows. Just as a teacher, I have to like look up and keep searching and searching to see where things came from. Whereas this shows you exactly, right? Like these two pieces of logic here come together, we combine them to get, and then it shows you what happens, okay? All right, so the next one's just going to justify, and then we're going to do a couple more proofs. I put, 3 more proofs. If you understand this, you can absolutely stop. I'm making this video one of the longest because proofs is something that people struggle with. So I really want to give lots of examples of me doing proofs, okay? All right, so let's do another one. So JK is congruent to LM, then LM is congruent. So that's the one we're not going to use much. That's the symmetric, saying you can reverse the order. And that's the property of, we're talking about congruence. So again, we're not going to use that much, but it's there. If AB is 14 and CD is 14, then they're equal to each other. So this could either be substitution, prop of equality, because we could just replace this 14 with the CD. Because these are equal, we could just substitute it in. But more accurately, that was supposed to be a circle. More accurately, that's the transitive. Or more accurately, more specifically, that's the transitive property of equality. If W, X, Y are collinear in that order, then that means that this is in between the others. So W to X plus X to Y. So that's the very definition of betweenness. Okay. If MN is congruent to PQ and PQ is congruent to RS, well then we can get rid of the middleman and say MN's the same as RS. That's the definition. Whoa, why did I say definition? That's the transitive property of, and then we're talking about congruence, so it's of congruence. Okay, if EF is the same as TU, and 2 totally separate letters. Oh, that's crazy. How's that going to help us? Oh, so see, we started with the EF equals TU. We started with that, and then what we did is we added GH to the left, and now instead of adding GH to the right, they added an equivalent value, BW. So this is just the additive property of equality, but it's a less used version. Usually we say if A equals B, we could add the same thing to both sides. But more generally, we could add 2 different things as long as C equals D, because they're not different things. They have the same value. And so you're still just adding the same value to both sides. But what that lets you do is kind of surgically carve different things off of different sides, and it lets you just be a little more flexible and adaptable. But it's still just the additive property of equality because you're adding equal things to both sides. If JK plus MN equals that, oh, then we can just get rid of that JK on both sides. Why have JK on both sides? So that's just the subtraction property of equality. Okay, good ones. Now let's do copy and complete the proof. So this one's already somewhat done for us. I find, again, this harder to follow sometimes because their structure doesn't exactly match mine because we're different people. So the given, you just copy these 2 statements down there. Okay. Then it says, I know that AD is equal to CE. That's because we knew they were congruent in the given. So that's the definition of congruent segments. Okay, and then we know that AD plus DB equals CE plus, so that's what we just talked about. So you start with AD and CE, and then you add DB on one side, and then instead of adding a DB on the other, you add an equivalent value. So still that's just the additive property of equality. It's just that more articulate, useful version, okay? Then the segment addition postulate states that piece plus piece equals whole. I'm guessing they're doing it twice. So let's do two separate things. So AD plus DB. So that's just part of the journey plus the other part is equal to the entire journey. This is all algebra. And separately, still with step D, they also said that part of the journey on the other one, or let's do it in the same order that it's written here. So CE plus E to B is equal to the entire journey from CB. Again, that's only if they're collinear and E is between, right? Then part of the journey plus part of the journey equals the whole journey. Then what lets you say that AB is the same as CB? Well, we have AB is equal to this, and we have CB is equal to this, and from the very step above, we know those two things are equal, so that's the substitution property of equality. Or you could think of it as two steps of transitive, right? Like if CB is this, and this long thing is that, then those two are the same, right? Like these two are the same by transitive. And then we do that same thing again. Well, if AB is the same as that, and CB is the same as that, then, so it could be two steps of transitive, or you could just say you did two substitutions in one step. So that's a substitution property of equality. And then here, if we have the segments are equal, well then we know they're congruent by the very definition of congruent segments. So that proof made a lot more sense following along. That was nice. Okay, so copy and complete the proof. I erased the complete the proof part because I want to do this one from scratch ourselves. So let's do green this. Green. We'll do some purple next. I like that. Okay, so we're given that WY. Oh, so that's hard to draw on the diagram, but we're given the entire diagonal here is equal to the entire diagonal here. So I'm going to just get rid of those. We're also given that A is the midpoint of XZ. Now, an assumption that people make is, well, if it's the midpoint of this, it's also the midpoint of this, which in this case is true, but those would have to be two separate statements, okay? Just because it's the midpoint of one, like I could have it's the midpoint of this segment, and yet it's totally not equal the other way, right? Like this is a length of 1 and this is a length of 5. It still passes through the midpoint of this other segment. So just know those are two totally separate questions, okay? So we know it's the midpoint, so I marked that these must be congruent. That's not the exact given. The definition of midpoint we have to use to get that they're congruent. Okay, and then we want to say that WA is equal or is congruent to ZA. Okay, yeah, this is good. Okay, let's start with A is midpoint of WY, and A is midpoint of ZX. Okay, so that's step one. I wrote both of those as step one. They are given. And then I'm going to use both those. I'm not going to use the other given yet. I'll use that one later. So I'll save that for when I'm going to use it. So now I know if they're the midpoint. So with the definition of the midpoint, which is, I mean, just big picture, it's the only way to get from words to a next step is by using the meaning of the words. You can't just, I mean, there's nothing else you could do. You have to use the meaning. So I'm letting you choose whether the midpoint says the two sides are congruent or whether it says that the two sides are equal. Now in this case, I know that we're dealing with pieces and a whole. And so I know we're going to use the segment addition postulate. Also, it's basically the only tool we've got so far. So I'm guessing we're going to be in the world of algebra here. So I'm going to choose to do, that means that W to A equals A to Y, and Z to A equals A to X, right? I'm just using like, put A in the middle, Z to A to X. And that's the definition of the midpoint, okay? And then I'm also going to go ahead and say, well, we know that, and I'm just going to use the segment addition postulate. So we know that WA plus A to Y adds up to the whole thing, right? And similarly for the other one, ZA plus AX equals the whole thing, ZX, right? That's the segment addition postulate. Okay, well, I can substitute. Like, why even have that? Like, I could I could put, well, let's not even get there yet. We'll do some algebra later. But what do we know? We know wy is the same as zx. So we know these two things are the same. So let's go ahead and state that, okay? So 4, we are given that wy is congruent to zx. Okay, so 4 was given. And then 5, we're going to turn that into algebra because that's useful for us to do some algebra. So I'm going to say, well, that means that wy has the same length as zx. That was the definition of congruent segments. Okay, and then that means step 6, what we can do is we can tie these together. So this is wy and this is zx, and those are the same. Then with 2 steps of of transitive, or 1 step of substitution, we can now say that wa plus ay is equal to za plus ax. Okay, so that was the substitution prop of equality. And now what I want to get to is that wa equals za, right? So I want to get that wa is the same as za. So I just want to get rid of this ay, and I want to get rid of this ax. But if we look up, what do we know about ay, right? What do we know about ax? Well, they're the same as that wa. They're the same as that za. So let's go ahead and replace those. Again, I'm going to use a different color because I find that useful. So I'm going to keep the wa and I'm going to swap this out. Plus, I'm going to keep the za. And I'm going to swap this out, right? And I'm going to use, again, the substitution property. Notice that I can use substitution multiple times. Again, it's for clarity. Don't do 7 steps of substitution in one, because then your proof isn't clear. And the entire reason for a proof is to clearly communicate a logical flow. So there was my substitution. And so now what we need to do is just a little algebra, okay? So for 8, I'm going to go 2 wa's. It's just a length. That's like saying 2x. Right? That's not a problem. So 2 wa equals 2 za's. Then I can divide and I can get wa equals za. And then lastly, if the lengths are equal, I know wa must be congruent to za. Or if we wanted to match exactly, we could write, oh no, wa, za, the order of letters did match. Okay, so then 8, how did we get from here to here? For me, I would say that's either arithmetic, or simplification, well, my hand did that, or simplifying, or definition of, really, that's like a definition of multiplication almost. Like, what is integer multiplication, right? 2 times a number means you add it up 2 times. So I'd maybe do like that's definition of multiplication almost, or you could call it combine like terms. So there's lots of things you could call this, combine of like terms, whatever. So there's lots of things you can call that. And the most common is just arithmetic or simplify. Okay? And then how did we get to here? Well, we divided both sides by 2. That's an operation. So that was the division property of equality, div prop equality. And then if we know the lengths are equal, then we know the things are congruent. And we got to there by saying that was the definition of congruent segments. Okay, wow, 10-step proofs. We're getting big now. Okay, so if we know AB is equal to BC, then how do we know AC equals 2 ABs? All right, so this last one, I'm just going to do a flowchart proof because I love flowchart proofs. So let's start. So if, right, this is the given, then that's the to prove. We have our diagram, right? So let's get rid of the if, get rid of the then, and we have the given and the prove. All right, so let's start with AB equals BC. Okay, well, I don't see how that's useful yet. So what else are we going to use here if we're talking about this segment and these things adding up? And remember, I can assume this is a straight line, 180 degrees, because it looks like it. Well, I'm going to go with the segmentation postulate. Again, it's one of the only things we got. We're definitely dealing with a piece and a whole here. So, oh wait, AC, yeah, okay. So let's start with the piece and piece. So we'll say from A to B plus the rest of the journey, B to C, is equal to the whole journey, A to C. Okay, that's the segment addition postulate. Okay, this was given. And AB equals BC. Well, I want to show that it's 2 BCs. So I'm going to combine these. And I'm going to get rid of the non-BCs, right? I have the AC. That's good. I have just a highlight here. I have the AC in this statement. Good. I have the BC in this statement. Good. I want to get rid of this, okay? So I'm going to undo that. I don't want that writing all over that. But I want to get rid of the AB. So how do I get rid of the AB? Well, I substitute it out, okay? So I'm going to use green here, and I'm going to say, well, then I've got something plus BC equals AC, right? And this is going to be the substitution prop of equality. And so I'm going to substitute in AB is actually the same as BC, okay? And then lastly, I'm just going to use that weird name step, arithmetic, simplification, and get, well, then AC is equal to 2BC, and we'll just call that simplify, or arithmetic, or combine like terms, or whatever. Okay, there we go. AC is the same as BC. Again, I think the flow here of a flowchart proof is so much more clear about arrows, where it goes, logical flow. All right, hope you enjoyed that video. Holy moly, longest video ever, 50 minutes. This is crazy. But I just wanted to do lots of examples. If you stuck it with me to the end, whew, good on you. Okay, all right, adios and good luck.